You know that feeling, right, when a car takes off and you get pushed back in your seat? Or that little lurch in your stomach in a fast elevator? Well, that feeling is acceleration. But in physics, it's way more than just speeding up. Today, we're going to dive into what acceleration really is and how we can actually see its story play out. So think about this for a second. Hitting the gas, slamming on the brakes, or even just turning a corner at a totally steady speed. What single idea connects all three of these things? They seem so different, right? Well, the answer is acceleration, and I promise by the end of this, you'll see exactly how they're all connected. So here's our game plan. We'll start with what acceleration actually is, then we'll get into why direction is so important. We'll break down the difference between average and right now, learn how to read the story that graphs tell us, and finally, check out some really wild examples of acceleration out in the real world. All right, let's get into it. All right, section 1. What is acceleration? You know, this idea stretches from something as simple as putting your foot on the gas pedal all the way out to the massive forces that shape entire galaxies. It's a fundamental rule of how things move, everywhere. Okay, so here's the official definition. Average acceleration is just the rate at which your velocity changes over time. And here is the absolute key thing to remember. Velocity isn't just about how fast you're going, that's speed. Velocity includes your direction, too. So if you change your speed, or you change your direction, or both, guess what? You're accelerating. And of course, there's a formula for this. It looks like delta V over delta T, which is just a fancy way of saying the change in velocity divided by the change in time. That's it. It's all about figuring out how quickly that velocity is changing. Now, the units for this can look a little weird at first. Meters per second squared. What does that even mean? Well, it's actually pretty simple if you break it down. Think of it as meters per second per second. It's asking the question, by how many meters per second is your velocity changing for every single second that passes? See? Not so scary. Okay, let's jump into our next section because this is where we need to clear up a really common mix-up. Most of us think of slowing down as deceleration, right? Well, in the world of physics, slowing down is still acceleration. It all just comes down to direction. Yeah, check out this quote from our source material. It says it all. When an object slows down, its acceleration is opposite to the direction of its motion. This is known as deceleration. So, you see? Deceleration isn't something different from acceleration, it's just a special kind of it. This really gets to the heart of it. Think of it like this. If the acceleration is pushing you in the same direction you're already going, you speed up. Makes sense. But if that acceleration is pushing in the opposite direction, you slow down. It's like a tug of war between your motion and the acceleration. Okay, let's walk through a few scenarios because this is super important. Say you're moving to the right. We'll call that positive velocity. If you also accelerate to the right, you speed up. Simple enough. But what if you're moving right and accelerating to the left? That's negative acceleration. You slow down. Okay, now for the tricky part. What if you're moving left? So, negative velocity. If you also accelerate to the left, negative acceleration, you actually speed up in that direction. And here's the real mind bender. If you're moving left, but accelerating to the right, you slow down. The big takeaway here is that to slow down, the signs for velocity and acceleration just have to be opposite. All right, let's talk about average versus instantaneous. Imagine you're on a long road trip. Your average acceleration for the whole day might be close to 0. But what about that one moment you floored it to merge onto the highway? That instantaneous acceleration was huge. See the difference? One's the big picture, the other is a snapshot. So yeah, instantaneous acceleration is exactly what its name suggests. It's the acceleration of an object at one specific point in time. It's what's happening right this second. And this is where it gets really cool. We can actually see this on a graph. If you're looking at a velocity time graph, the instantaneous acceleration at any given moment is just the slope of the line right at that point. The steeper the line, the higher the acceleration. If the line is totally flat, that means 0 acceleration. And that's a perfect lead-in to our next section, how to read the story in the graphs. Because that's really what they are. They're not just data points. They're like a visual storytelling telling you the entire journey of an object's motion. It all connects in this amazing chain. You start with the graph of your position over time. The slope of that graph tells you your velocity. So now you can draw a velocity time graph. Then you take the slope of your velocity graph, and guess what? That gives you your acceleration. Each one flows directly from the one before it. And believe it or not, it works in reverse too. If you have an acceleration time graph, the area under the line tells you how much your velocity changed during that time. It's like climbing back up the ladder from acceleration to velocity. Pretty neat, huh? Okay, so let's put all this theory into practice and look at some real-world examples. Now that we know what we're talking about, let's get a feel for the scale. And trust me, the numbers can get absolutely insane, from a gentle cruise to some of the fastest movements on the planet. Just look at this table. A normal elevator ride, that's about 2 meters per second squared. You drop something, gravity pulls it down at 9.8. But a baseball getting walloped by a bat, we're talking 30,000 meters per second squared. The scale here is just huge. To really get a sense of this range, let's look at two totally different ends of the spectrum. First up, a high-speed train. It eases into it, accelerating at a nice, smooth 0.25 meters per second squared. Super gentle, very controlled. Okay, now for the other end. The jaws of a trap-jaw ant. When they snap shut, their acceleration is, wait for it, 1 million meters per second squared. Let that sink in. We went from a gentle train to one of the fastest movements in the entire animal kingdom. That's the mind-blowing range we're talking about. And look, this isn't just fun trivia. Understanding acceleration is absolutely critical. Scientists need to figure out how cosmic rays accelerate to protect our spacecraft from radiation. They need to accelerate particles in giant colliders to discover the fundamental secrets of our universe. This stuff has major real-world implications. Okay, I want to leave you with one last little puzzle to chew on. Can an object have zero velocity, meaning it's completely stopped, but still have non-zero acceleration at that exact same instant? Is that even possible? Take a second to think about it. The answer is yes, absolutely. Think about what happens when you throw a ball straight up in the air. Right at the very top of its flight, for just a tiny fraction of a second, it stops. Its instantaneous velocity is zero. But is it still accelerating? You bet it is. Gravity hasn't gone anywhere. It's still pulling that ball down at 9.8 meters per second squared, getting ready to yank it back to the ground. A perfect little paradox that shows how velocity and acceleration aren't always doing the same thing at the same time.